Hi everyone, I'm sorry for being a little late, but I hope right now we can start the lecture. And today we will talk about very important topic in time series data, on how to analyze one-dimensional data. And by the end of this lecture, I hope you'll be able to tell on your own what's good and what's bad about this particular problem statement. And for example, do we need a neural network to deal with this type of models and with this type of data. I hope you enjoyed the first lecture, but if you have any complaints or questions, please don't hesitate to contact me or, for example, Evgenia Romanenkova and so on. Also, I advise you to turn on the cameras because it helps me a bit to understand what's going on the other side of the screen. So 1 minute and we will start. I want to remind you that at some moment during the lecture, I will make a screenshot of people who is there to check that are you here or not. Okay, so finally, we will now try to introduce a class of stochastic models in the simplest possible case for our data. In particular, we'll consider the case when we have some signal and some time, and we observe signals that varies with time. Okay, we can think about anything simpler when we are dealing with sequential data. In real life, it's for sure can be more complex. And one example here is that we have a lot of signals out there. And in this case, we have multidimensional time series or multivariate. But many basic things we can see even in the case of univariate, which we focused right now. Another type of additional complexity we can add to the data is say that we have not as like structured data, like tabular data, but with some sequential feature related to time, but rather a figure each time we observe something. So we have some catch, I don't know, another catch, and so on. And this image is a sequence of images that we do typically with neural networks. Another layer of complexity. Another thing we can think about is that sometimes our observations are not uniform in time. And in this case, we can also try to bring some help from neural networks that can incorporate this variety as an additional feature. We can try to use simpler approaches if we, for example, interpolate and say, okay, let's imagine that we have some uniform grid of 1, 2, 3, 4, 5, and so on. And we have some observations here, not uniform, but rather some strange points in between. But we can try to find some approximation in between and deal with this data and imagine that this is time series we are working with. But let's start from the very beginning. And today, I hope you'll be able to cover the simplest case and cover the most popular and most efficient approaches to work in this case if we want to create models for this kind of sequential data. We'll start with some motivation and what kind of problems we want to solve. Then we introduce the simplest possible models. And after that, we will have like additional layer of complexity, but it would be for good because this stationarity assumption and after regression moving average model, at first I hope hear it about them a lot before this course, and in the second place, when we are talking about something like this, we can bring some kind of theoretical justification on what we are doing and why we select one model or other models. If we will have time in the end, I also have a couple of slides of what we can do if this kind of approaches doesn't work, but still we want to get some useful thing about our time series. From the very beginning, we assume that we have a lot of time to look with this time series data and to try different transformations for them. This is because all the models we select here are based on observations and on looking into data. And so if we have like millions of time series and we want to construct millions of models, it would be hard to apply something like this, but at least we can try here. So what's the motivation? Why we are doing this kind of stuff and what kind of problems we want to solve? Okay, we can imagine, for example, maybe a bit wrong motivation, but at least it works at many layers. And it brings to the table many problems related to time series data processing and time series data models. Okay, we have this index of top 500 of companies at United States stock market, and we see the dynamics of this stock market. And you can see that we have here, I think we have daily prices here. And each day we observe a price and we want to somehow create a model for this data. Maybe the simplest model we can imagine is something like smoothing of the data we have. But for sure, we can imagine different problem statements and different models. So at first, what in our terminology, what's modeling is trying to bring some structure in the data to reduce the dimension. And basically, any model we introduce in machine learning, and not only in machine learning, is somehow a simplification of the situation we have overall. Because instead of whole data we used to explain to describe a situation, we instead use like very compact representation of what we build with. If we think about linear regression, it's also a model and it's also a compact description of the data. Instead of this whole table, we see that we can describe the correspondence between input and output as some kind of a linear model. And this coefficients exactly is a way to compactly describe the data. So we will try to do something like this, but for sequential data. If our models are simple enough and you understand what's inside them, it provides you with another possibility, another opportunity, interpretation, what kind of thing we observe. For example, we can think about as interpretation, some seasonalities, or some trend in the data, and so on. We can say we observe linear trend, so it's quite probable that in the future we'll have something like this, and we have even further increase of the target function and so on. And this kind of thoughts bring us to the third point here, maybe the most interesting thing back there, trying to forecast the data from the past observations. It's okay, we try to imagine what's going on next, maybe with some confidence intervals and so on. Okay, this is very basic things, and a lot of people are doing something like this. It's very basic methods, but also you can imagine different problem statements related to this sequential data. When you forecast something, the next step, the next desire can be to control the behavior. If you observe some like GDP growth or this line, and we are a central bank, we can try to control this behavior and balance unemployment rate and GDP growth and so on. So if you have some variables to change, we can also include them in the model and try to provide some kind of simulations on top of what we had before. Also, we can try to somehow look at all the stuff from a different point of view and try to test some hypotheses. Do we have some seasonality, for example? Do we have some training? Is time series stationary? And so on and on and on. And last but not the least, quite useful in some situations, is simulations. We can think about this as either a simulation of what can go one can occur with time series. For example, we can imagine that we have some different scenarios for the future, and we try to compare them and estimate our risk overall. Also, we can look at this as a generative model. If we have some distribution, probability distribution that describes the data, we can try to use the distribution to generate new data or to fill the gaps in the data and so on. And this kind of simulation is also kind of useful in many applied problems. For example, if we have some time series forecasting approach on top of all this, but we have some missing data in between, we can try to fill this data with a generated model and then go on with forecasting with these generated features if we are doing everything right. So this kind of problems we want to solve, and let's provide a couple of examples related to this kind of behavior. And so let's start with the first data set, in particular about monthly sales for a souvenir shop at some town near the beach on the coast of Queensland. And you can see that, okay, we already have some structure in the data. We don't have only like some random points. It's not a random noise. It's typical sequential data and gradually increase. We have some trend here maybe, and also maybe some seasonality. That each December near the Christmas season, we observe peak in sales of souvenirs because a lot of people are visiting this small town in Queensland. And we can try to use our simple observations to provide a model. At first, we do some pre-processing. Typically, we use some log scaling of the data. And after it, we are able to have some models for trend. So here we see that this logarithm has linear behavior, linear growth. When we go from the left to the right, so this shop is maybe quite successful. And also, if we look at the residuals, what's the difference between the trend and our observations? We can observe some seasonality, which we also can model with something like this. So now we have some explanation for the data, some interpretability of the model. So we have this peak in the end. We have this line of sales in January, because maybe no one goes to this small town in the beginning of the year. So we provide what I will call in this presentation a classical decomposition of time series by T to trend, to seasonality, and to the remaining part we can't explain, and what we typically consider as the noise. We can say that we can interpret our model, and this definite seasonality can help us to make decisions and to explain on what is going on here in this shop. And also we can move to the next step, and for example, to predict sales for the next year, to plan the logistics related to delivery of the souvenirs from like a great store to a small shop in a small town. And this is what we can do with this kind of data. And this is time for me to make a screenshot of what people, okay, are here. And also please write in the chat that you understand everything at the moment and you don't have any questions, okay? Thank you. Thank you a lot. Okay, but let's go back to our content. Okay, in this case, we assume that we have this like initial time series, we have trend, and we have seasonality. And also we have the last part, which is the noise here. A good question, because we will need this kind of notation a lot in this lecture, and maybe one of the heaviest with respect to amount of formals we have in this course. So please don't hesitate to ask some questions if we come to some strange place you don't understand. So let's consider another example, maybe less related to you, maybe because of, maybe less. Okay, so another data set we consider as an example for a lot of problem statements we can bring. Here is a number of unemployed people in Australia from 1994. We also can try to do similar things. So we have this dependence on number of unemployed people with respect to, I suppose, monthly data. And we have like something like, I suppose this is the top value we have here. Also, we can see some baseline. Also, we feel that we don't need any transformation of the data. We don't have any missing values. So you just start with the step of modeling the trend. Again, it's reasonable to start with a linear trend. And if you feed this linear regression, because basically it's something like yt equals at plus b, and this is a linear dependence of the output, our signal, on the time with some coefficients a and b, we can adjust, we can estimate with the data. So basically it's like a linear regression when we're doing this kind of estimation, and we see that definitely observe some trend. Also, we can try to deliver some seasonal variation. It also like very simple model and does not require hard work to estimate this kind of things. We can say, okay, we have this yg, we have this trend xt, at plus b. So we have residuals yt minus xt. And so we can imagine that we have seasonality, yearly seasonality, because we have 12 months in 1 year, and we have some observations for each month, each year. So we have yt plus 12, yt plus 24, and so on. And we have corresponding residuals, rt plus 12, and so on. And we can, for example, can estimate the seasonality related to a particular month is the mean value rt plus 12 times tau, for tau from 0 to how many years is the data we have. In this case, we have 1, 2, 3, 4, 5, 6, 7. Yeah, 7 years. So it should be like this for this data. You can see that we're doing this manually, and we use kind of expert knowledge of what kind of seasonality we observe here. So basically we can have this in this similar form with trend, seasonality, and noise. Also, we can imagine that we have the dependence on external variables. For example, we have like CT observation, GDP, or maybe some weather forecast for this particular month, for example, mid temperature, or maybe some other decisions we can make, and so on. And so again, for interpretation, it remains the same. We have some seasonal adjustment to the data. Again, we can forecast and like continue the trend, continue the seasonality to predict an unemployment rate in the future. But from this, we have something new because we have these additional variables. So we can try to add a layer of control to make the unemployment rate similar to what we desire, and to control some variables to make the target variable move in a certain direction. Also, we can try to look at this unemployment rate at a global scale, scale and try to find some correlation between global warming, for example, and unemployment rate. I'm not sure if it will work or not, but at least we can try. Okay, in a very basic thing, we can say, okay, we have this additional variable. We assume that we have a linear model, so fCG is some coefficients like C times G, where Cg is CO2 emissions. And we basically have again a linear model because we have a linear dependence of target with respect to the input variable. So we can apply hypothesis testing based on linear regression models and test if C is not zero or C is zero. And so we can say from this, is there any effect on unemployment rate from CO2 emissions? Not sure. Okay, if this would be a strong result, a strong correlation, but maybe we can find a better example for this kind of things. Also, we can try to do some kind of simulations on top of this, and we can try to move, like to observe and to generate some scenarios, some cases related to this unemployment. And again, we can move away from this particular problem and consider something more general, estimation probability of catastrophic events, for example. So you see that it's pretty natural to look at time series as this, to split it to parts, to look at different parts of the data and so on. So we have this powerful tool to directly use that what we have now is time series, not something very different from this. So now let's try to dive deeper into time series models. And again, it will deeper our understanding of what general problem we solve and what models we introduce to solve this problem, because we don't have a lot of data usually to model. Okay, you can observe, okay, from this data, from these examples, you have not a lot of points. Okay, you have 7 years and 12 months each year, so it's like something like 84 points in total, and you understand that you can't have a lot of features here because you will not be able to estimate linear regression coefficients related to them, and it would be even harder if you consider a more complex model like gradient boosting, but you still need models for this. So our ultimate goal is to specify the distribution of the data we have. So you'll be able to tell the probability of yt1 being smaller or equal to z1, y tk being smaller or equal to zk, and so on. So this is like very general model. And for sure, because we don't have a lot of data, and there is not many models actually to model the joint distribution, we mostly take a look into the first and second order moments for this distribution for particular times. So this is like mean value each time. This is the correlation between two values here. And also typically we will start from even square models right there. And gradually we will increase the complexity of models to capture more and more effects related to time series. So the simplest model we can have here is white noise. Basically, we have no assumption about the connection between different y's, and each y is generated from Gaussian random variable with zero mean and some variance sigma squared. So about this moment, we paid attention at the previous slide. We say that the mean value is 0, the variance is sigma squared. So basically, we can directly write this joint probability distribution as a product of separate probability distributions for each time moment. And as you can see, okay, it's very simple model. As a Gaussian random variable, like it's easy to write down the density related to each particular time moment. But what is bad? This model is almost useless. It basically says that what we observe is just noise. There is no connection, there is no sequential nature in this time series. Each time we observe a new variable, it's like completely new. We can make a strong assumption about the distribution of the last yt given all other y's in the data. Practically, if we look at this formula, we can say, okay, it's like this. So, yes, you can calculate this density, but no, you can't make this density sharper or more precise if you look at previous observations. Okay, nice model, useless model, but I think a good point to start. And actually, it can be useful too if it is one component of our data. If you say that we have some trend and some noise, it's like can be typical assumption for noise to be white noise with some variance we estimate from the data and 0 minutes, kind of natural thing. But we can see that this white noise is only a part of what we model, something we can't explain, and it's like natural that we can't explain everything, but also we can say that we can't make any predictions of this. So we try to make more interesting models, and like one step more advanced model is a random walk. Here we can see the Gaussian random walk, and this means that the signal yt is equal to the sum of these guys. So basically we have at each time step some observation of epsilon t from Gaussian distribution here, and we say that we go either up or down. Here we again assume that we have this discrete nature of the data. We generate our signal, actually a realization of our random process at each separate time moment, and we don't have anything about what's going on in between. In this case, we also can try to make some linear interpolation. Basically, we don't know. This model is kind of useful because it assumes some structure, and basically it makes very strong assumption about what is going on in the nearest future. You can say we can get everything we need from the previous observation. So if you want to predict yt, and we know yt minus 1, then okay, we can, I think I'll do have the slides here. No, we don't have. We say that this distribution, okay, can anyone say what is the density, the conditional density of yt given yt minus 1 and yt given y1, yt minus 1? Given this. Okay, let's select someone to answer this question. And for example, let's ask Polina Karpikova to try to guess about the distribution.
Two distributions.
Okay, we have this we have this assumption that our model is a random walk. We generate each next yt on the base of adding a random noise at each time step. So we are interested in distribution. This is a conditional distribution p of yt given yt minus 1, what will be the density for this distribution?
Yt minus 1 plus
Plus what?
plus 0. Oh, sorry, plus probability of epsilon t.
Okay, so this would be like a distribution like that. Yeah, from what family would be this distribution?
Normal distribution.
Okay. So what is the mean value of this distribution would be?
0.
Are you sure?
No.
Let's make another guess. So we know yt minus 1, yeah? And we know that this is like non-random variable. So we want to have an expectation of this guy. And this is what we know, yeah? So what's the expectation of this sum?
Yt minus 1 expectation of.
Yeah, because like the expectation is linear with respect to sum, and we can decompose the sum of two expectations. This is not a random variable. This random variable is 0 mean according to our assumption. Yeah. So here we have this mean value, and what is the variance?
One.
Why?
Because variation of yt minus 1 plus epsilon t is 0 plus variation of epsilon t.
Yes, the independent. So okay, and also this is not a random variable. This has 0 variance. And so what is this variance is this epsilon t. So it's like this. Thank you, Paulina. This is the correct answer. And also another question for the audience. What is the distribution of yt given all previous observations? What is this guy?
I mean, it's the same.
Yes, why?
If we know n t minus 1, it already incorporates all the knowledge about the previous variables.
Yes, exactly. If you write down this distribution, it would be like similar to this. So like they're equal. And we can say that this is like Markovian property that holds in this case for this random walk. And it's easier, it's like much easier to model the data like this than trying to model a multi-step conditional distribution, because in this case, the model would be much more complex and much more harder to deal with. So we can say that in this case, we have some structure in the data, sequential structure. And if you look at the next observations, they are completely defined by one nearest observation. For example, we can try to write something like this to t minus k, and we can say that it would be also Gaussian distribution with mean yt minus k and variance k times sigma squared, because we add k independent ID random variables with 0 mean and the variance 1 from a normal distribution. From properties of normal distribution, we can do something like this. Okay, again, we have something more useful that describes, for example, stock prices of successive days, on how a molecule travels in a box, in a liquid, and also it's kind of, if you consider two-dimensional random box, it's the best for an animal like in wild west or in Africa. And so you can see that if you bring more structure, we can make more conclusions about the model. So this kind of conditional distribution we derived here can be used for prediction And so this mean value would be like the best value we predict if we consider the mean squared error here. It's quite easy to show, I hope, because of this quadratic term in Gaussian density and so on. Okay, so we can make this kind of models more and more complex, incorporate more and more terms and some assumptions about the time series we have. But basically, often we can come from a slightly different direction and say that we have these two types of behavior we want to model, and we should introduce the description of the model for each of these. We have trend here, and we have seasonal component here. And the simplest model we can have for trend model is a linear trend, so it can be like this. Now for seasonality, we also can decompose it into a basis of functions, and maybe the simplest basis we have is as a base of trigonometric functions, cosines and sines, with some coefficients and some frequencies. And so if we estimate this lambdas well, then we again have a linear regression problem, which we can estimate from the data. And also we have this third term, typically just ID white noise in most cases. So if we look into more details related to trend model, we can see that, okay, it's pretty easy to model things like this with a formula like this. And for seasonality, we can also have estimation, which looks quite nice. And if we have a sum of trend and seasonality, we have kind of nice model, interpretable, all the stuff. So this is like basic, maybe more heuristic model than what we have before. Okay. If we want to have a more general procedure, we can have this sequence of steps. At first, we can try to look at time series. It's always a good idea to look at the data and try to make some assumptions on the basis of what time series looks like. For example, do they have some missing data, trend, seasonality, and so on. And basically, like, this is what we usually look at, but maybe we can have some peculiarity specific for your particular data also. As in other machine learning problems, we look for outliers, but typically it's hard to deal with them. Also, it's another useful trick to make the data series stationary, and we will discuss a bit later why do we need this assumption and how does it work here. And if we have this stationarity, we then estimate trend and seasonality. Also, we can apply nonlinear transformations to make it stationary. And also, it's also a good idea to look at prediction, not YT, but instead something like this, for example, this first order differences, and maybe anything else, because it makes data look more structured and so easier to model. And also sometimes we have residuals with some particular structure, and maybe you have some features that can be used as external features. So we can try to do something like this, and we can imagine some model related to the residuals that we have, like f of CT before. So we have this pipeline, these typical steps we apply to have the model of multivariate errors, univariate time series data. I will give right now some examples, so you will have a feeling of what's going on at each step. And why is it important? At first, it's kind of useful to have some preprocessing. And typical preprocessing for many data series is logarithm. We have this kind of initial data, and we have very different scales here and here. And it's hard to have the same model that works well at all the scales. So you take a logarithm transformation, that now like the difference between here and here is like not orders of magnitude, but rather like from 7 to 11, so it's like 4 instead of 10, I suppose 6 power. So make such transformations to deal with the data. Another idea, very useful, is to take differences because it's usually much easier to see some structure in differences. And also we kind of reduce some kind of trends here. For example, if we have linear trend, so if we have pi t that equal to at plus b, then we have the difference that equals to a. So it's a constant. So instead of a harder model like this, so you need the coefficient to estimate, and also you have some non-trivial trend here. You can instead consider a simpler dependence, so you don't need to model such complex trend, but the predictive power of this model is the same. If we want to predict something, we predict, okay, we have the last value, we predict the difference, another difference, another difference. So you can sequentially make forecast of the future in a way similar to what we have for initial time series. Also, we can try to do this kind of thing multiple times here. And so we can say that we have like this third order differences, k order differences here. And if we say that we model our yt is a polynomial of the power k, so we have not only component by beta 1t, but also beta 2t squared and so on. In the end, we can reduce this problem to the problem with the constant differences. So instead of modeling this coefficient separately, like we reduce the problem to the case where we don't have this dependence on time after k differentiated. So basically we have this g1, g by t is g1 by t minus g1 by t minus 1, and so on. And this way we define delta k, and we have this model here. Also, when we are modeling stationarity, we also can write down some formulas to provide clear explanation of what's going on. We define the difference with the lower index as the difference between trend here and trend g times ago. Also, we have some seasonality component, but we assume that these two guys are equal, so this is just 0. And also we have this difference related to noise, which we usually don't care too much about. So we can write down all this as formulas here. So I hope everything is clear. And if it is, please write again plus sign in the chat. Okay, if not, please ask me something. I will be glad to answer your questions. Okay, thank you for your feedback. And let's go on and try to make another couple of models. And basically to introduce after regression moving average model, we should start with stationarity. series, how to make time series stationarity, and what is it exactly. So basically, we say that time series is stationary if, if there is some not much difference between the behavior in the past and behavior right now, in the present, but instead of this vague definition, we can try to limit ourselves to some kind of mathematical definition of stationarity. We can say that time series is strictly stationary if we select some k, some set of indexes, another set of indexes, window size. Then if we have this joint distribution for the first set of indexes and we shift everything by h for the same z1 and zk, that this distribution coincide with each other. So basically, if we consider behavior here and behavior here in the future, then we can use the same probabilistic model. It's kind of strong assumptions. And if we have linear trend, for example, we don't have the stationarity because we have the shift in mean value here, and so we don't have this equality for the probability distributions. But in many cases, for example, for white noise, we can say it's stationary. And also, let's try to make it a bit simpler right now. So we have a general definition of strict stationarity, but we typically consider only first and second order properties. We are not interested in this whole complex distribution. Instead, let's try to look at mean value and after covariance function. For mean function, we have this mu t is the mean value of yt. So each without noise at each yt, we have this mu. We assume that these variances are smaller than infinity. Mean value is also smaller than infinity. And also we introduce another guide after covariance function. It's what is left when we substitute the y with y minus mean value here and here, and we have the covariance. It's after covariance function because we don't have different features. We have the same feature y, but at different time moments. So we define the second order properties as the covariance function, and we look at this after covariance function to describe the stationarity. So we say that we observe weak stationarity if the mean value is independent of t, so we have no this obvious trend, and also you have the second order properties. The link between yt and yt plus h is similar to y tau and tau plus h for any t and tau, and also for any h we don't have this different behavior. So we can say that, okay, if you have some yt, then in h steps we have some distribution, and it would be the same distribution if you start not from yt plus 1, for example. It is the same. It means that we have weak stationarity for mean value and for the after covariance function. It's also much easier to replace the true index definition of after covariance function with one index, because we say, okay, we can reduce t and we have the same function independent of t. So it depends only on the window size. So it's kind of how big is the spread of random variable if you start from some point. And this is what was different, what we should define here. And so our after covariance function is only a function of h. I hope everything is clear. Yeah. And we can move further and try to define some additional things that kind of useful for time series analysis. At first, I would like to introduce the after correlation function here. this is the ratio of the function gamma, which we define it as after covariance function. So instead of covariance, we define the correlation by dividing gamma y of h by gamma y of 0. And this is like correlation function here. Also useful. So let's do some simple exercises, some examples on how the stationarity can look like in simple cases. We start with this guy. And okay, what's the name for this guy? Can someone answer me? Have you considered this type of model before in this lecture? Can write in the chat. So constant zero mean, constant sigma squared variance. Okay, make additional assumption about that the distribution, yeah, is Gaussian, and we have white noise. We have no dependence on the time here. So mu t, which we're looking for, is 0. So it's a constant, and we can meet the first assumption. Yeah, good. Also about the second assumption, about how after correlation and after covariance function look like. We can say, okay, if t does not equal t plus h, so h is not 0, these two, yt and yt plus h, are independent from each other by our assumption, because it's ID noise. So we have 0. If we have h that equals to 0, then we have yt and yt plus 0, so yt, and we know that the expectation of yt squared is sigma squared, and we can see it here. As you can see, we meet the second condition for the random process to be weakly stationary. So we have this weak stationarity for white noise processor. Okay, simple model, simple answers, but quite good answer here. Okay, let's try to make something similar about random walk and see if it is stationary or not. So basically, we have 0 mean for each yt, because we start with the sum of independent Gaussian random variables with 0 means. If we have expectation of sum of random variables, it equals to sum of expectations, sum of zeros, so 0. For variance as the independent, we know that variance of sum of independent variables is equal to sum of variables for each of these guys. Each of them is from Gaussian distribution of 0 mean and sigma squared variance. So we have t of them with equal variances. So sigma t times sigma squared. So we have this type of variance here. So if we are trying to compute the after correlation function for t plus h and t, it is the covariance between yt plus h and yt. So basically, if we go back to this formula for yt, we add this additional terms here. These guys, new noises, are independent from what we observed in the past, but these two guys like equal to each other. So we have 0 expectation for the product of epsilons after time step t and yt. So we have the remaining part here, covariance of yt and yt. And because the mean is 0, we calculated like this, and we have this guy here. And as we can see, for mean value, we have 0 mean, so it's independent of t. For after covariance function, we don't have this independence of time. It's set because for this time series, it's not stationary. But we can easily proceed and replace this non-stationary model with stationary. If we consider yt plus 1 minus 1 yt, we have now it is equal to yt plus 1, epsilon t plus 1. And this is basically white noise we have at the previous slide. So in this case, these differences help to make time series stationary. So this simple trick works, and generally using the bag of tricks I described before, we can make time series more stationary. So again, we reduce trend, we reduce seasonality, we somehow take differences, and after that, we hope that we will have stationary of the time series. Okay, so this was the Taylor-Bar stationarity, and why it is important, because it's again much easier models. You don't need to model this all kind of dependence here. You just need one function that decreases, typically decreases as time passes. This is like basically yt h. And so if we have stationary time series, it's much easier to model this kind of time series. And later we will provide an example of this type of models after regression moving average. Okay, any questions up to this moment, guys? If everything is clear, please write down a plus sign in the chat, and we'll continue in 1 minute. Okay. I think basically we kind of have this for ARMA, and I hope that we answer part of your questions later in GitHub. And if not, okay, we can switch to this regime we just tried during the previous lecture when we just have this model as G for dependence on variables for trend, but basically, typically we don't have this kind of discussions because of it's much harder, and we usually for this simple data sets not have enough data, and also we have little time in our course to deep into much details here. Okay, so let's consider another random process, which is called moving average. In this case, we assume that each yt is a sum of two terms. The first term is epsilon t, the second term is epsilon t minus 1 times theta. So theta is like kind of parameter for our time series, and each epsilon t is like a Gaussian random variable, they are independent of each other, so this basically white noise. So we, from this basic building block, white noise, try to construct more advanced process that has more explanatory power. So we again do some math and start with calculating the mean value. As mean value for each epsilon is 0, if we have sum of two epsilons, we again have 0. So mean of yt is 0. Also, for gamma y, this after correlation function, we should calculate the mean value of yt plus h times yt. Yeah. So we write down the exact formulas for these guys, and we know that if these points are too far away from each other, then we have one epsilon, another epsilon, and another two epsilons. They don't intersect. So if they're too far away, then it's just zero. But more interesting case, if they're not far away. If h is plus minus 1, then we have like the two terms that intersect. One with the coefficient theta and one without any coefficients. So if we calculate the mean value of theta yt squared, we have theta sigma squared. Yeah, and this is what we get here. Okay. Also, we can have like similar t's is h equals to 0. In this case, we have both terms that works. One terms have coefficients 1, so we have this part, and another we have two thetas. So we have an expectation of theta epsilon g minus 1 epsilon g minus 1 times theta, and we have theta squared times epsilon g minus 1 squared, so it's theta squared sigma 2 sigma squared. So basically we have this function, and as you can see, it does not depend on h, on t. So we can say that the mean value doesn't depend on t, and covariance function also doesn't depend on t. So we observe stationary time series. So we introduced another more complex model, which has the name of an average, and is very basic, that allows this kind of representation. Also, we can try to introduce another important one. So this is moving average, and this stands for the last part in this ARMA abbreviation. We will introduce this first model on this dynamic noise behavior. It's kind of strange after correlation function. So basically, we can say that we have some non-zero correlation here, then here, and then everything else is 0 when we are talking about the value of h. This is 1, 0, 1, minus 1, 2, 3, and so on. So we have exactly 0 correlation. It's okay in some cases, but sometimes, and it's most typical scenario, we observe more complex correlation, which has non-zero values if we go 2 or 3 steps away from the dependence. So we need another model to describe this type of behavior, and this type of model is after regression here. So if you look at ARMA again, we consider it moving average part of the model, and now we consider after regression part of the model, RF. And if we consider first order after regression model, first order because we look at only one term in the past, so it's the same for moving average 1, we look only one, the first term in the past. We can say that each y is yt minus 1, so previous value, times some phi plus, again, white noise process. If we assume that yt is stationary, which is equivalent to phi smaller than 0, then we have this requirement for the mean value and from covariance value. For mean value, we should have equal means for neighborhood y's. So we write down mean value for yt. It equals to phi times mean value for yt minus 1. And we need this equality to hold. Okay, either phi equals to 1, which is not the case because it's too strong assumption, because in this case it would be increasing variance on and on, you'll have something like random walk behavior, which you don't want because it doesn't lead us to some stationary behavior. Instead, we say that this mean should equal to 0. So this is our first thing to do. And regarding the second moment, we again, from the independence assumption, write down the expectation of yt squared. It equals to phi squared times expectation of yt minus 1 squared plus variance of the noise. And again, we should fulfill this stationarity requirement. This guy, A, should be equal to, for the next time step, because we should have equal variances. So, okay, we have this A 1 minus v squared. Phi is smaller than 1, so it's a positive term equals to sigma squared. So A equals to sigma squared times 1 minus v squared. And we have this requirement for the stationarity. So for this time series, we have this expectation here. If we look at the covariance function, we can guarantee that now we have a stationary time series, random process. Then we again write some formulas. So we say that if we have h steps to do, we add, okay, we can decompose it like this. We take phi away and we are one step closer to yt. We repeat the steps one more time and so on and on. We repeat the step for h times. And now we have this guy here. So this guy is what we already have here, yeah. So basically we produced the after covariance function for after regression of the first order random process. And we can look at some examples of such time series. For example, after regression 1, a random process is phi that equals to 0.95. We have some connection between neighbor points, but it's not very strong. If we, okay, but it's quite, excuse me, it's quite strong. And okay, we have this slow motion from one part to another. If we reduce phi, we would observe something quite similar to a Gaussian random walk, but not YZ. We also have some connection here. We can introduce also multiple steps. You can say, okay, yt is not only phi by t minus 1, but also we can incorporate phi 2 by t minus 2 plus some epsilon t and so on. If you have two terms, the name of this process after regression of the second order is two phi's to estimate, and we can produce more interesting behavior here if we need it for the modeling of more complex processes. Again, we can try to estimate this after covariance function. Why do we need it? Because as we introduced two random processes, two models, we should somehow check if these models are good for our data. Is the structure of the after covariance function is what we expect from our data? And so we measure this empirically after covariance function. We again assume stationarity. So we assume that we have dependence on h, but does not have the dependence on t. And we have something like this. If we have this sample empirical after correlation function estimation, so basically I had h, this is h here, then we have only one non-zero germ that we have for white noise. And all the correlations should be smaller, typically smaller than this threshold here that's related to like some 0.05 significance level as far as I can remember. And so if we try to look at more complex models, as we looked at white noise, and we have zero sample after correlation function if we have h greater or equal to 1. For trend, we have flow decay. You can imagine that, okay, we have yt equal to at plus b, and we definitely have some gamma gh of neighborhood values here. If you have periodic structure in time series, then for sample after correlation function, we have another type of non-stationarity. We have this peaks for the periodicity, for example, 1 week, 7 days, for example, here. If we consider this random process we introduced a couple of minutes ago, for moving average, we have zero after correlation function after some moment. For after regression, we have exponential decay to 0, and you can do it on your own. So let's look at some examples, some pictures. For trend, we have this linear dependence, for example, and we have this slow decay to 0 as we consider for high values of h. If you have some periodic time series, again, we calculate the after correlation function and have it with this nice periodic structure with peaks when we have this delta that equals to the periodicity of time series. We have delta, 2 deltas, and so on and on. For moving average, as we discussed, we have a structure like this here. And for after regression, we have this exponential decay. So basically, this after correlation function serves as a tool for diagnostic, and it can say us what kind of models we should expect and how can we fix non-stationarity in the data with the right selection of normalization or of the model itself. Also, if you look at ARMA process, we have this assumption here. So these guys come from after regression part, and this guy is this dynamic noise. Again, we build on top of white noise, but we have no assumption. If we have only after regression part of the process, then we just say that we left only with white noise at the right hand side, and we can minimize the squared error with respect to coefficients of phi y to phi p for determining the parameters of after regression process of order p. We have this p order here. Well, in the master form, we have this simple linear regression assumption. Okay. This is what we can say about after regression. For moving average, we can also opt for some maximum likelihood solutions, but we will not discuss it right now. We also can say that we can provide more complex model for after regression part. We can assume that this is some parametric function plus some noise. This is after regression, but instead of the linear function of the previous observation, we have some nonlinear function. And so we train this guy using a regression approach with a naturally emerging sample of points to do this. And in this case, it's kind of useful to apply any linear regression approach, and it works like a charm in most scenarios because linear regression like works in almost all scenarios too. So what we actually looked today, we tried to provide a more or less general framework for modeling of univariate time series when we observe one time series and want to introduce some model to it. It happens that we can try to introduce some models on the basis on what we see. And typically, it's a good practice to look at time series we want to model and say, okay, it's a white noise. Don't bother me with this kind of problems. Don't model it. We can predict anything. Maybe we can say something more complex about random walks, or we can try to decompose time series into stationarity or trend, seasonality, and some noise. And it can help you to get a better model for the solution of, for example, time series forecasting part. And it's essential for this theory that we should deal with stationarity here. If time series is stationarity, then everything is good, and it's just we coined with the right model. Also, it makes sense to think about it as some like more general model, and typical more general model is after regression moving average we discussed a bit later. Okay, you can ask me a question, what is ARIMA, another name here, and we have this another letter here integrated. And it means that we consider not y1 by t, but we made a simple transformation. We consider x1, xt with x t equals to yt minus yt minus 1. This is integrated part of the first order. If you consider like second order differences, 1kt, we have integrated of order k time series. And also one last fact is that there is some theory behind it. We have Volt theorem that says that if you have a stationary time series, then we can decompose it into the sum of independent components, linear sum of independent components, independent white noises. So basically we can derive this ARIMA model, and it would be the best model we can get if we are talking about a stationary time series. So that's it for today. Thank you for watching and for asking some questions. Unfortunately, not many of them, but I hope for more in the end. This lecture was kind of mathematically intense, I would like to say. And later, I think we would have less formulas and less assumptions, less theorems, because we will move into the value of neural networks. And in this case, we don't have much theory and much statistics to deal with. But I hope you will be able to understand what I told to you today. Also, during the seminar, you will try to do the decomposition and to try some stationarity tests on your own. So good luck with the seminar. Have a good day and goodbye for today. See you next class.